So thank you very much for the invitation. Very nice to contribute and participate. So my talk is on exciton dynamics, light harvesting in Photosystem 2. And particularly with a view of finding structure. And this is perhaps an unusual goal, but I will show that finding structure is, in the case of PS2, essential for assigning function, particularly the fundamental processes of charge separation, energy transfer. That's really the case, and I will demonstrate as I go along. Now, in my group, almost everything we do is meant to find structural information for ultra-fast processes, and we use different methods. And today I'm going to talk about crystal spectroscopy as well. Now, one first comment I can make, it's not necessary to have oriented samples, such as crystals. For instance, you can analyze a symmetric and antisymmetric stretching frequency of, say, a carboxylate group by IR spectroscopy, and it's very well known that this is exquisitely sensitive to equilibrium geometry in terms of its bond angle, its bond lengths, and deviation from pure symmetrical geometry. And it's sensitive far better than anything you could achieve with X-ray crystallography. This is an interesting point. However, you are doing one chromophore at a time, and not every chromophore of interest can be analyzed in this particular way. We have in the past used these things to look at structural dynamics on picosecond timescales. So then for the question of exciton dynamics, can we use ultra-fast crystallography? The very short answer is no, not today. And I will need to select optical methods for this particular problem. Therefore, with optical methods, it's even better. If you have spectroscopic information and you can add to structure, then that's really an advantage beyond just structure or just dynamics. And in my talk, I'm going to discuss experimental work on femtosecond IR studies of crystals, and in addition, I will talk about what we are doing at the moment, which is extending this work to do measurements in the exciton basis, and that needs visible light, and particularly crystal measurements of nonlinear electronic spectroscopy that we are currently building, and I want to discuss some of the implications of what we need to do in order to transfer this methodology from the single site basis to the exciton basis. So that will be included. It's useful to revisit what has been done traditionally for decades now in ultrafast spectroscopy of photosynthesis. You would do a pump probe transient absorption measurement, and with photosynthetic particles, you would typically, over timescales of femtoseconds to a nanosecond, retrieve perhaps a handful of time constants that are orthogonal, as shown by SVD or global analysis, and that means that you can explain any spectrum at any time point with just linear combination of 5 basic components. Yet we know that with pumping chlorophyll A, in the case of this is PS1 data, but we have very similar PS2 data, that they contribute up to 100 pigments in there. So that is not necessarily the best type of analysis. You can do things they were first developed by Alfred Holzwarth. You can do a conversion, a direct transformation of experimental data into so-called lifetime density maps. And then perhaps you can argue for a distribution of time constants that each have different spectral signatures, and that's fine, but the bottom line is that ultrafast spectroscopy, it does not have structural information, and it does not have information at the level of single pigments. But even worse, if we are honest, after decades of all these measurements, nobody really agrees on what it means. The real issue, if you drill down, is that if you have a set of coupled differential equations that is used in target analysis, you cannot prove where is the bottleneck. Target analysis tries to recover the intrinsic rate constants for reversible reactions, and in the PS2 field there emerged two different examples. And I will come back to this. Only structure will solve the problem. So that's the traditional approach. So to find structural information, let's say you are doing a two-color experiment, in this case a visible pump, IR probe, then you measure the IR anisotropy, and it does contain structural information. The molecular information is in there, but it's adjusted by the optical anisotropy that is caused by a finite bleach effect if you use femtosecond visible pulses, which can be retrieved, but all they are angles between vibrational and electronic transition dipole moments. In the literature, you will find determination of an electronic transition dipole moment by making assumptions on the vibrational one or the other way around. So all you have is a single angle, and it's not in an absolute frame. And certainly we have worked on creating extensive sets of photo selection data in the past and making analysis of directions that can be fitted on the basis of calculation. And in doing this, I want to quickly mention that this is a few years ago. We collaborated with Gaussian, and we worked on the problem of how do you retrieve dipole gradients in proteins. And this is a multi-layer technique, and for the first time we executed true analytical frequency calculations in this multi-layer onion technique. And so they're true analytical. That means you have analytical second-order gradients, and the technique itself is an extrapolation method. I refer you to Mike Bearpark, my colleague at Imperial, who I worked with. But effectively, you get energies, but also frequencies and dipole gradients by extrapolation technique. And these results, they have a problem in the sense that there will be degeneracy, meaning that if you have two frequencies that are the same, but one is on the moon and the other one is on planet Earth, they're not coupled, but they will look like mode mixing. So there's a problem there. But still, these theoretical results, they appear to indicate that even for a high frequency mode, say a CO stretching mode, that there will be ready mode mixing with protein environment. And so structural analysis, even of such oscillators, might be a particular problem for structural analysis. And that's, when I recently look back, that's still the state of the art at the moment in quantum chemistry of analyzing the vibrational delocalization length of these oscillators. So that's also a piece of information that goes into the problem. And now I want to introduce the method of two-dimensional electronic spectroscopy that we are currently developing. So this is a field that's been developing very rapidly in the last 10 years or so. And there's many new groups entering this field, and many of them work on the problem of photosynthesis. What you get from nonlinear electronic spectroscopy is like an NMR spectroscopist, you will retrieve frequency-frequency correlations. And so a cross-peak will tell you you have two coupled chromophores. It's an electronic measurement. And the excitement in this field at the moment seems to be centered all around the fact that coherences, long-lived coherences, are seen at room temperature. And there's discussion on what it means. That's not necessarily for me the interesting part, but my objective is to use two-dimensional electronic spectroscopy as a rigid and critical test of structure-based theory. And I will come back to this, to plug the gap between analyzing structures, coordinates from crystal structures, and using spectral simulation.
as a test for this. This here shows some figures that if you calculate the crystal case, then for the polarization response you get for different point correlation functions that I will explain in a moment. You will get these patterns, and I've selected here only the biaxial class of crystals, and then as the frequency changes, these patterns will rotate and do that rapidly around resonance due to anomalous dispersion, and that's just a practical aspect. Now, in the language of nonlinear spectroscopy, it is said that the response function formalism, it solves the density matrix to third order, meaning there are 4 interactions. Now, for NMR spectroscopists in the room, this is, let's say, light entertainment, because we are just describing Bloch sphere dynamics. That's really the method that's being used in response function formalism. And let me just go through this, what it means, because it is my method to get to exploiting the crystal environment for extracting exciton dynamics. So these pictures, they are Feynman diagrams. Richard Feynman worked in electrodynamics, and he invented these pictures to show what is going on so that you don't have to look at an equation. And so you look at the picture and you can see what's going on. There's a time progression. You start in the bottom and you end up on the top in the progression of the dynamics in the system. Inside are the relevant density matrix elements that you can put direct notations. And these arrows, these are the field dipole interactions, and the direction of the arrows is what we say the phase matching condition, which is the experimental directions of the pulses that you combine, where the fourth field is the emitted field that's detected on your detector. So that's more or less what it means, and these are 6 basic types of response functions that I've written for only 2 coupled oscillators. They expand to 28 types. And then I'm giving this figure in this particular way that each response function that solves the density matrix is scaled by a so-called 4-point correlation function that puts the electric field and dipole interactions all together. Now, you can imagine that for isotropic samples, there is a straightforward geometric calculation to retrieve the magnitude of the coherence contributions, which in fact are to some level experimentally addressable. And about 15 years ago, Robin Hochstrasser calculated these. You use Legendre polynomials. This is then the start of using this methodology to look at crystals. Because in crystals, of course, now the 4-point correlation function becomes a symmetry progression. And so with expanding these response functions to 28, then you have to use the Van Neumann principle to use the point group symmetry, of which there are 32, to calculate the 4-point correlation functions. And then for each response function you can have up to 81 tensor elements, which are either non-zero or 0. In doing this, I actually discovered that if you are looking at calculation of magnitude of coherence, then if you express it in the basis of the solutions to Maxwell's polarized wave equations, you simplify everything. I can do the whole set in just 10 pages of equations. And this is just background, just to give you that, to illustrate, just in pictures, how I use this to analyze. Like an NMR spectroscopist, we make 2-dimensional spectroscopy measurements. These are simulations. And so I have a little toy model. I put 2 coupled dipoles, and they are 90 degrees aside. If I choose a C4 symmetry, then I can choose an orientation in the unit cell of these dipoles to coincide with the crystallographic direction, and then the symmetry progression, as I predict, will sum the response functions that contribute to the diagonal peaks to 0. And so this is not what you would see in solution. And if I then do these simulations, then indeed there are only diagonal signals, and their amplitudes are perfectly balanced to sum to so-called absorptive spectra. But this looks completely like two isolated oscillators that are not coupled, yet they are, if you see what I mean. I can place the identical dipoles in a completely different orientation, and suddenly there are cross peaks, but this diagonal peak is missing, and we have line-shaped distortions that I can understand from writing out the phasors in these response functions that are due to summing phase twists in these. And so you can see that even for this simple toy system, it does look rather complicated, but this gives the basis for analyzing nonlinear methods in crystals. And you can immediately see that Photosystem 2 is a completely different ballgame. That's 74 chlorines, of which some are strongly coupled in exciton domains. And so that is the major challenge. So I'm working with a leader in the field of structure-based analysis. That's Thomas Wenger. And he is at the moment developing methods for structure-based simulation of nonlinear spectroscopy, and we are collaborating on this, and the goal is to put this 4-point correlation function analysis and that I've developed into this theory as well as a critical test, because the simulation based on coordinates that he is producing can be tested in solution, but it's much more determining in the case of the crystal environment, because I have found a method to select on the basis of structure and orientation the contribution of each coherence contributing to the nonlinear signal. And that's new. So that's a bit of a background of what I'm doing now. Oh gosh. We've recently worked on femtosecond IR measurements, which are results in the single pigment basis. You need an experimental method where you have to prove diffraction limited performance. That's what we've done. We are very lucky with the orthorhombic symmetry in PS2 crystals, because the principal dielectric tensor corresponds to the crystallographic axis in this case, and these are Maxwell's wave equations for this symmetry. And all this depended on knowing precise index. So we have to do crystallographic indexing, because in the case of biaxial systems, this is ambiguous on the basis of birefringence analysis. So we know that we are making measurements in the 1, 0, 0 plane. I'm just speeding up here because we know eventually that what we put in our spectrometer are tiny crystals. They are only 3 microns thick, where we make transmission measurements, and we know everything about their orientation. So now we are analyzing the 2-point correlation function response, which is the linear response that is invariant across all these symmetry operations in the unit cell. And so we analyze the asymmetric unit that has a non-crystallographic symmetry that we can see in the data is time dependent as energy transfer goes on. I mentioned Thomas Wenger. Thomas Wenger started developing a structure-based theory of exciton dynamics, and I believe he started this when he was with Rudy a long time ago, and he has continued to develop this. And the challenge in his field is the parameterization of the exciton Hamiltonian, which means the site energies for each and every of the 74 chlorines in the dimer of Photosystem 2. Then he has a very elaborate essentially density matrix calculation with a set of master equations that include Redfield theory for exciton relaxation and generalized Foerster theory. And I asked Thomas, can I use your theory? And can I use your methods? And I was able to modify his theory and code for the crystallographic case, where I'm now representing the 2 unique solutions to Maxwell's polarized wave equations that correspond to the crystallographic axes, and these movies here are now decays of contributions to the excited state decay during energy transfer in two different starting populations, whether I have polarization along one crystallographic axis or the other one. So that's what the theory predicts. And this now plots this in the single pigment basis because we are doing an IR measurement, and so that works as a projection of the population in the exciton basis. We now return to the issue of vibrational delocalization. We are looking at the polarized response of keto stretches. By coincidence, there is, if you do an isolated chlorophyll A harmonic frequency calculation, the transition dipole moment associated with the CO stretch has only a few degrees angle with the TD-DFT direction. And so you are using this keto mode, this oscillator, as a projector of electronic excitation. And if we assume this to be fully localized, then you would have a time zero dichroic difference in the crystallographic case because it's ordered, and you are picking out a particular photo selection amplitude, and this matches prediction and experiment. And you just rotate the polarization and the spectra completely change. You measure very different spectra in two directions. Interestingly, it's almost independent of where you start with in initial excited state population, which you can control by polarization. The end result is the same. Photosynthesis is marvelous in that it is so flexible, the yield is always the same, and so the non-crystallographic symmetry is developed in time through transfer through to the red pigments. And that's what we see. We can make comparisons of experimental probability amplitudes for the IR measurements and then calculation. And there are, this is very interesting, we're not making a very precise comparison in the sense that we have no assumption on frequency in the case of the population, and we have no direct measurement of population in the case of frequency. But we can make these comparisons, and we can do a selectivity analysis for finding out which of these probability amplitudes match best by comparing the two dichroic differences. Now, to return to the problem of this discrepancy in ultrafast spectroscopy of PS2 after decades of pump and probe. Basically, two models can predict the exact same fluorescence decay. And one is completely different from the other in that one is called the exciton radical pair equilibrium model. It assigns the dominant 60 picosecond decay to reversible charge separation. It says the trap is extremely shallow. Alfred Holsworth says there's a 0.02 electron volt difference in free energy for that trap, and energy transfer is super fast. And he's always assigned a few picosecond dynamics to energy transfer that we now believe are exciton relaxation dominated processes. That's the RP model. It's survived for decades. Based on analysis of structure, and this is led by Thomas Renger, he proposes the other way around. He says that because of the distances, the bottleneck in open reaction centers is the overall transfer from CP43 and CP47 to the RC. And here's the functional part. The delta G for the charge separation in open reaction centers, if QA is not reduced, is such that it's essentially irreversible. It's 170 milli-electron volts, I believe, and the rate is 6 picoseconds. So in that case, the overall bottleneck is the transfer to the trap, and then trapping is irreversible. It won't come back. But now, under strong light conditions, you will start to reduce QA, and you generate closed reaction centers. You want to protect the photosystem. And then what happens is that excitons at least 50%, if not 2/3, can escape from the trap under these particular equilibrium conditions. And then entropy-driven, the exciton energy is removed to low-energy sites. And these are now identified to be distal from the RC. They're sites in CP47 particularly. And that's where the excitation energy then ends up, where it can safely radiatively decay. And that's now the interpretation, the functional interpretation of placing the overall bottleneck in the energy transfer from the antenna to the RC. And it could only be decided on the basis of single crystal measurements. It's the only thing that plugged the gap between structure-based theory and ultrafast spectroscopy. I will skip the final bit because I also solved the P680 plus VU fight-in structure in the presence of non-crystallographic symmetry. And this was a very small team. All the experiments were done by my postdoc, Marius Kausikas. And with Thomas, I worked for many years. And this took 7 years to publish and understand to the point that we arrived at this conclusion. And I would like to thank Jim Barber, who has given me the confidence to start working on his beautiful crystals and this particular problem. And Karim and Nora has also been involved in this project. And I would like to thank you for your attention.
Terrific stuff. New, opening doors, still worrying about photo protection at the end. Are there any questions? Yes.
I noticed in the introduction you mentioned the P2 moments of the orientational distribution. Since you have a two-photon system, absorption and emission, the P4 moment should also be possible to obtain, right?
Is this the photo selection case?
Yeah.
So the photo selection case, you just use the second order Legendre polynomial, which is then in the ensemble distribution, the anisotropy directly. So that's fine in linear response.
Mm.
Yeah.
It resembles something I heard from Robin Horstrasser, his optical spin echo method. Is it related to that?
Spin echo?
Yeah.
That's not analyzed. It's a photon echo.
Yeah, but I mean, it's corresponding to the NMR spin echo.
It is corresponding.
Yeah.
That's right. As I said, the evolution of the density matrix that's analyzed in four-wave mixing is Bloch sphere dynamics eventually. Yeah. And so we use very much the same terminology and mathematics, which helps a lot in doing this for the first time in this case.
I should have read the paper, Jasper, but which chlorophylls are the most red-shifted are the ones that actually fluoresce, potentially the sites where you would have...
So the protective sites, you mean?
Yes.
I think there. I think that's the one. But it's in the paper.
Thanks.
Yeah.
I have an experimentalist question. That is, have you thought about starting with a very simple reaction center? Crystal?
He's not allowed.
So we do the difficult things first, but no. I mean, I wanted to do the simple thing first, which is the choice of the single pigment basis, and that's why the IR crystallography was so successful, because I knew instinctively that working in the exciton basis straight away was going to be too challenging, and very often when I give this talk, I'm asked, why didn't you do it in the visible? And so that's why I give this explanation. I first needed to do the, I think, much more simple IR analysis. And so I'm now ready. But we do need simpler samples in the sense that if they're more homogeneous, then they will allow me to test the validity of this analysis much better. And we are doing this now.
Very good. Anyway, pioneering stuff, Jasper.
Thank you very much.
Okay, James.